Transportation in plants. So this is lesson 5.2, 5.2a. Yeah, we'll get going. That should be distributed to everyone, so let me know if you don't have that. I think I sent out, in fact, I think I sent that one out on Monday. So what we want to talk about is, we know that the first level of categorization that we talked about when we looked at plants was we said that some plants have transportation systems and other plants do not have transportation systems. Does anyone remember the name we used for those? We say that plants that do have transportation systems we called vascular. Good. And then obviously those that don't have them we called non-vascular. Not very exciting name. Okay. So we discussed that most plants are vascular. Let's define that term below. We're just going to say vascular plants have cells that are specialized to form vessels to transport fluids throughout the plant. So a vascular plant is one that has cells that have been specialized to form vessels that will move fluids throughout the plant. I'm going to do my attendance because I'm a responsible teacher like that. Okay. So while I get the attendance done, I want to think about this next. What materials need to be moved around in a plant? So in the space below, I want you to put some stuff. I want you to do some brainstorming for me. What is it that we are actually moving around a plant? What materials have to get moved around? Stop. So if you are a plant, what has to go through your vascular system? What is it you need to be moving? Oh, sorry, Sam is not here. Mess that up. Michael is not here. Okay. Okay. Talk to me. What do plants need to move? What are the things they're moving around? Yeah. Good. So nutrients. For sure. So that could be nitrates, that could be, oxygen, CO2, things like that. Sure. What else do they need to move?
I put metals.
Metals. I'm going to put it. Talk to me.
I've heard that literally every living being on the planet has at least a little bit of metal in it.
Yeah, that is true. That is true.
Do they remove metals?
Yeah, they do. I mean, they do in the same way that we do. Like your cells need your muscle cells need calcium. That's an important part of muscle movement. You know that your bone cells need calcium. Just your regular cell maintenance involves sodium and potassium, so these need to be a part of your diet. And I am not super well versed in plant physiology, so I can't speak to what specific metals they would need, but definitely some of the nutrients they need would be metals for sure. Metal ions are an important part of what cells do. So yeah, I'd agree with that. What else do we think? I like those. What else? Come on.
Water.
Water, definitely. So specifically, plants move water. In fact, plants move a lot of water. So I like that. Water is going to be one of the big ones. I'm going to write it real big. Can we think of anything else?
Maybe soil, earth.
Yeah, I'm going to say components from the soil, definitely. So I don't think the soil itself moves up through the plant, but things it takes out of the soil, yeah, for sure, definitely. Interestingly, what did we say the product of photosynthesis is what? So a plant takes in carbon dioxide and water, and up in the leaves it undergoes photosynthesis, and it makes what? That's a waste product, that's true.
Energy for...
Yeah, and what form of energy do plants make? Sugars, yeah, good. And the sugars that the plant makes in the leaves, do they only stay in the leaves? No, of course not, right? They have to be moved throughout the plant, so they get moved. So all of these things are going to move in there, but also you know this, you know this from your own body, which is if your body wants to send messages all throughout it, if your body wants to send a message to one specific place, we typically use our nerves, right? Like if you want to send a message that says to my finger, move, that goes along a nerve, right? From the brain to the arm, boom, move that. Does that make sense? But if we want to send a message to our body and say, hey, all of our muscles, tense up, get ready. Or, hey, all of our muscles, let's relax, slow down. How do we send those messages in the human body? Do you know? We talked about briefly when we talked about animal systems. It's not one of the systems we focused on.
Like the way it passes through all?
Yeah, how does your body send messages to the whole body?
The electric shock?
Those are the nerves.
Oh.
And those are more specific. But to the whole thing, to just say, instead of trying to send a message down every single nerve to every single muscle, if we just want to send, what's something in your body that goes everywhere anyways?
Hormones?
Hormones in the blood. Does that make sense? And that's why we have hormones that say relax. We have hormones that say get tense, get ready. But they are like general messages that get sent throughout the body. Well, plants do similar things. They can use the transport system to send messenger molecules. So, for example, if a plant has been damaged in one spot, it can send throughout its transport systems molecules whose job is to say, hey, we're damaged, let's protect ourselves. Plants have systems like that as well. So the vascular system of a plant has a lot of work to do. Does that make sense? It's got a lot of things it does. It moves nutrients, which includes components from the soil, which includes metals, it moves sugars, it moves water, it sends messages. So lots going on. Now, direction matters. Direction matters because keep in mind, what is it, for the most part, that is flowing? What is actually moving through the plant? Well, in your body, how do we transport stuff? What flows throughout your body? Blood. And blood is primarily, what makes it move is that it is made mostly of water. Good. And how do plants move things throughout? Well, by moving water. Yeah, not even just plant water, but just good old-fashioned water. So it is water that moves throughout a plant. Hi, Mr. Kubek, how are you?
Hey, I'm doing well. We're learning about some high-quality H2O here.
That is right. I wonder if they get that reference.
Bobby Boucher.
Bobby Boucher.
Good movie.
Ah, see, there we
Hey,
go.
he's got
There
it.
we go.
Yeah, so just quickly, how about displaced student?
Oh, yeah.
You have.
I do. He's in
Water boilers with Adam Sandler.
Water high quality. He is probably the best participator during lessons. He gets things, he totally understands material. So he is not out of the game. He's got lots
Yeah,
of
Happy Gilmore was the
Any
girl.
chance,
Billy
because
Madison's
he's
the
out
school
period
one.
trench, any
Is he?
chance he could on period floors come here and work on science and math? You can see your numbers are crazy big, so,
No.
yeah, okay,
He can work in here.
yeah,
Absolutely.
yeah.
Yeah, send him
That
down.
would be more benefit to him, and if he has a question, you're.
I'd be glad to have him. Yep, send him down. It's water that moves through a plant. Now, in general, where does a plant's water come from? Where in the plant does the water come from? The ground. So in the plant, where does it come from? Yeah, and what's at the bottom of the plant? The roots. Good. So as a rule, the main flow of water is upward. Right? So if we have a tree like this, and it's got roots like that, look at my beautiful roots, and there's the ground. As a rule, water flows up. From the ground through the roots up. And if we're talking about a tree, it would go up the trunk of the tree, up the branches to the leaves. Now here's the problem. Is the only way we want to move things up? No, sometimes we want to move things down. So there is a secondary system to move materials down. So basically, you can think of a plant as almost like having a big conveyor belt that moves most things in one direction. From the bottom of the plant, from the roots, up to the top of the plant, the leaves for the most part, in most cases. Does that make sense? But then there's a few secondary pathways that can move stuff backwards. What is the most common thing that gets made up in the leaves that has to move down? What gets made in the leaves that we're going to have to move down the plant? Sugars. So this is the challenge of a plant then. We need to know how to move materials up through the plant and to build a secondary system to move it down. And to do that, we have two basic types of vascular cells. All right. So we have one called xylem. Xylem. It's a Z sound, but it's an X. Love the English language. Xylem. So these cells move water up the plant. trying to remind myself. I know I was going into detail later on. I'll mention this now. These are actually dead cells. They grow, they get into place, and then they die because they want to form kind of rigid tubing. So in xylem, the plant basically makes piping. We'll get into it more in a minute. And the other type of cell is called phloem. These names kind of suck, but here we are. Xylem and phloem. Phloem is responsible for multi-directional flow. And these are living cells.
Hey, Mr. Ryan.
Hey, how we doing?
I'm gonna come back and take your.
No, what's up?
Well, I just got a quick question for Kid and Resource.
Who do you have?
Abby Kneppel.
Oh, okay.
It's about they're finding magnitude of star, or not magnitude.
Here, I can pull up her work here. All right.
Oh, this one right here, I got it.
Just quickly, she is in my SNC 1D. Oh, this year's, not last year's. And Abby Knuckle, and she is working in space, and she's on Philip. Can tell us, is she on brightness and distance?
Yeah.
But he should be, there he is.
Okay.
Riley's here, okay?
Yep.
So
So
thank
she's
you.
this big one here.
All right, have a good
She's
one.
done that. She's done that right. This
Yeah.
way.
Okay, so what she can do is, up here we know the apparent magnitude, which is how bright it appears from Earth,
Mhm.
and that's 1.16. So we can put that in here and say it has an
Yeah,
apparent
we've got
magnitude of
we got there.
1.16.
How do you get the
And the
absolute?
absolute magnitude she's going to get looking at the HR diagram, which she did. So in the HR diagram, we can compare the temperature of the star to how bright it is. And so she came up with, which came up with 9350. She'd say the temperature is roughly 9350, and that would be perfect. And then you want to follow the main sequence. The stars mainly fall. So any answer in here would be reasonable.
Okay.
Try to plop it in the middle. And so that's a luminosity of 34.9 times the sun. And expressed as a magnitude, that is 0.913. So it reads right here.
Okay.
And she did slightly differently, which is totally fine. So she came up with 0.590. Totally fine.
Works.
Nothing, yeah, that's right. So she's got it on, like there instead. Like that's perfectly reasonable. So if you plug that into the calculator,
Away we go.
I don't expect them to be able to do the math, so this does the math for them. And so we come up with the distance of about roughly 42.5 light years.
Thank you very much.
No problem.
Sorry
And
for
then-
stealing your education, kids.
Hardly. And then she can Google the actual values here, which should be really easy to find. What does she have formal head? Yeah, that would be an easy one to find.
Okay.
And she can compare the two.
Perfect.
Does that make sense?
Thank you very much.
Cool.
Oh, now you're here? All right.
How we doing? Welcome. You are welcome to grab a chair in here if you want. If you don't want to listen to me talk about biology, you're welcome to grab a seat in there as well. Whatever you prefer. So
Sit back there or not?
yeah, you can sit back there if you want. Yeah, that's fine. Totally fine. All right, sorry about that, guys. So now, when we talk about xylem, xylem is kind of cool stuff. So the first thing we want to focus on, and I know we said it above, but it only moves water up. So is everyone ready to see some beautiful art? I know I am. So here is my plant. Okay, can I in my practice note, I drew a really nice plant that I was really pleased with. And the problem is now I have to try to repeat it. Okay, so say I had, there's a leaf. Oh, see, it already sucks. I'm so sad. Okay. You know what? I'm doing my best. It's the best I can do. There it is. Hey, this has like a fibrous root system. because the root system is fibrous, should I do like parallel lines on the leaves or should I do branchy lines on the leaves? I wonder if anyone remembers. Which one of those pair together? Does anyone remember? Yeah, as a rule, if something has fibrous roots, it's a monocot, and as a rule, monocots have parallel veins. Tend to have more of a taproot, right, with larger offshoots like that, and they tend to have networked veins. Not a big deal, but since we're drawing here, so they only move water up from the roots to the leaves. Of course. All right, so water would start down here, it's going to move there. This motion is constant. A plant is always doing it. Though the rate can be adjusted. So, no matter what, a plant is always moving water up through its xylem. Has to happen constantly, no matter what. And there are three things that make this happen. There are three different factors that make the water move up. All right? So the plant controls this really at three spots. The first spot is down in the roots, where it's getting the water. Where else is going to be a control spot, do you think? The leaves. We'll talk about that. So the first thing is called root pressure. And this is an active process. And when I say active process, I mean the plant has to spend energy to do this. It takes energy. Where cells in the roots pump water into the xylem. And the xylem, just so you know, we're going to talk when we get to the kind of anatomy bit at the end, but the xylem cells basically these cells form tubes, and then they die, and what you're left with is essentially the plant equivalent of like the pipe you'd find in your house. They just make tubes that go up the plant. So it's an active process, and the plant uses energy to move water from the surrounding soil into the roots. And this builds up, well, if you put more and more water into the roots, you're going to build up pressure. Good. This builds up water pressure. And the pressure is going to move the water up. So that is the first factor that makes xylem flow work. The reason we're able to get flow of water up the plant is that the roots themselves act like a pump, and they're constantly pumping water into the xylem, into these cells. And these cells are a tube, and as the pressure builds, because you pump more and more water in, it just moves the water up. Now, having said that, if we relied only on positive pumping, it would take a ton of energy to move water up. Does that make sense? So we try not to rely just on pumping. We try to make nature our friend. Does that make sense? For example, in our water systems, water pumping stations, water is actively pumped, but we put them at high locations. Why would we put water pumping stations that have to pump water to our cities and stuff in high locations? Well, because then if we need to get water to low-lying locations, what helps us get it there?
You don't need as much pressure.
Yeah, why not? Because what do things naturally do? They naturally move? No. Down, right? So for us, when we want to get water to a house, it makes a lot more sense to put our water pumping station on the top of a hill than it does to put it on the bottom, right? Because, and that's why, for example, water towers, which are there for if, the water pumping system fails, so we'd still have some pressure, we just take a bunch of water and we just put it up really high. So if we need to use it, what's going to pull that water down and send it to everyone's house? Just gravity. This is how the Roman aqueducts worked, right? They would get springs up in mountains, and then they'd build tubing down to their cities, and water would flow because gravity. The problem is a tree doesn't need water to go down, it needs water to go up. But that doesn't mean nature can't help us, because of a second thing called capillary action. So, to start this, we need to understand xylem makes tubes. All right, small vessels that move up the plant. Now, in grade 9 or grade 10 science, do you ever put water in a test tube? Maybe you took chemistry with me. Is anyone here taking chemistry yet? No, right? Get excited. If you put water in a test tube, does it sit flat like that? No, what does it do? You ever seen this? I mean, I guarantee you've seen this. Have you ever paid attention to this? If you put water in a test tube, it actually goes like this. It actually curves. Have you ever noticed that before? Even if you put water in a big glass, the water is mostly flat, right? But right at the edges, it curves up a bit. You ever seen that? And if you put water in a narrow enough tube, it will really work its way up the sides. Does that make sense? Well, if you make the tube narrow enough, the reason this happens is that water has what we call cohesive tendencies. It wants to stick to the surface of the vessel it's in. It sticks to the sides. Does that make sense? Water is attracted to the vessel it's in. So water has cohesive tendencies. If a container is narrow enough, the water can climb the sides of it. This is called capillary action. If time permitted, and maybe, who knows, maybe we'll do this today just briefly. I have some capillary tubing in the back, just very, very, very narrow glass tubing. And you can actually see this. If you put it in water, water will work its way up it. We can actually see this because I have a glass tube here that is a little bit narrow. Normally it has a closed bottom, so I had to break it, so it's a little sharp, so let's be careful. But if you look, if I put it in this container of water, obviously the water should come up to it at the same level, right? But let's see what actually happens. What do you see? Yeah, so much so that, is it at the same height as the water?
No,
It's way higher. Why would it be way higher? That doesn't seem to make any sense. I promised the tube was empty when I put it in there, and yet the water in it is higher. It's higher because of capillary action, because it's attracted to the side of it. Can you see that? And to prove that I'm not lying, here it is empty, right? When I put it in, it goes higher, right? And if you put a straw in there, a bigger one, it wouldn't do that. The narrower it gets, the more it's able to climb the side. The narrower you make the tube, the more it climbs. So you can look, empty, a few drops now. Essentially empty tube. I put it in. Oh, and now there's an airlock. One sec. If you get an airlock, it won't work. So we put in, and look how high that water's gone. Wow. Way, way, way higher than the water level of the beaker. Can you see that?
Yeah.
Substantially so. That's capillary action. And again, the narrower you make the tube, the more that happens. So instead of having one big tube, as xylem, what the plant does is it has tons and tons and tons of really narrow tubes. And then because the tubes are narrow, capillary action helps the water move up the plant. Does that make sense? This is a good design. It's also a good design because that way, if you get a hole in a tube, you've only damaged one small percentage of your water moving ability instead of the whole thing, right? Does that make sense? So it's a pretty logical system, isn't it? So we could say xylem forms a bunch of very narrow tubes instead of a single tube. That glass tubing, by the way, we use in chemistry to do melting point determinations. We put a chemical in there, a solid, and we load it into a machine that just heats it up and we see what temperature it melts at. That's a completely unrelated thing. Okay, so the first thing happens down at the roots, where we pump water into the xylem. And that moves the water up because it gives you pressure. The second thing happens in the xylem itself. The way the tube is designed helps water flow up. It's a good design, right? The third thing happens where the water is going. And you already told me where the water is going is the leaves. The leaves of a plant are the end point of water flow. That's actually how the water gets out. So we'll talk about that, transpiration pull. So xylem eventually leads to the leaves. Ah, bless English, where the plural of leaf is leaves. Why not leaves? No good reason. It's just how we do it. So, xylem eventually leads to the leaves. The end point is an opening in the leaf called a stoma. Here, water can evaporate into the air. What does it mean to evaporate? Very good. Okay, ready for some amazing art? It's going to be good. Is everyone excited?
Yes.
Okay, ready? If we have a leaf, all right, so here's a leaf. Hey, I want green. We have a leaf. There's my leaf. And we've got, these veins, and the veins look like that. Hey, is this a monocot or a dicot, do we think?
No,
Hey, what would its roots look like?
not fibrous, it's
A taproot. Very good. Okay, if we were to look here, what we would see is this. Here is like the surface of the leaf, and then we've got this vessel that eventually goes down all the way to the roots. Like big path to that, but does that make sense? This is like the surface of the leaf. This is like a side view. Does that make sense? And then this here is the vein. Okay. So here's the thing. This is packed full of water molecules, right? Water molecule, water molecule, water molecule, water molecule, water molecule, right? In a big long stream, right? One stuck to the next, stuck to the next, stuck to the next. And then what happens when they get to the top? When they get to the top, they can evaporate. And as they evaporate, they actually float away. Does that make sense? They become a gas. Can you picture that? The water basically forms a big column. And then at the top of the column, one of those molecules can just float away. They get caught up in the air and they float off. That's evaporation. Does that make sense? And evaporation, if you left a glass of water out, you leave it long enough, what happens to the water level? Decreases. Not boiling, it's just the top layer is able to get carried off by the air, and if that happens enough times, the water level works down. Right? That makes sense? Cool. But here's the thing. As water molecules evaporate, and move away, they pull on the molecules below them. This is because water has cohesive forces. Which means what? What is cohesion? If something is cohesive, what does it mean? Our team is really cohesive. What's true about it? We said it's adhesive because it sticks to the walls of its container. Adhesive means sticking to something else. Cohesive means it sticks to itself. It's attracted to itself. One water molecule has a pull on all the water molecules around it. When we take chemistry, we'll learn that this is the result of something called hydrogen bonding. This is actually a tremendously important force. It means that as the plant loses water, that force of evaporation pulls the water below it up along with it. So water leaving at the top helps it come down. You know this works because you have made use of this property too. When do you use this exact same principle? Oh, you all do it. You have a tube with water in it, and you apply a force to the water at the top of the tube, and it moves the water all the way from the bottom of the tube with it. Come on. When have you used a tube full of water where you apply a force to the top of the tube of water?
I forget what it's called.
Damn it, people, no you don't.
Something like that.
Yeah, come on. It's a straw. It's a straw. It's a straw. Yeah, no, you know how this works. For a straw to work, I gotta get a container that isn't like a chemistry container. So I'm gonna get a cup. How's it going? Okay, the hardest you have to work to use a straw, whether you realize it or not, is when it's empty. Right? So when I put it in here, right now there's a bunch of air in there. And at first, I have to work a little bit hard. I have literally managed to pick a straw that has a hole in it. That's great. That's great. I think when I was exclaiming, "It's a straw," well, snapping it around, I broke it. Okay, so when you first use a straw, it takes a fair amount of work to get water to the top, right? But now that I've done it, when I pull on the water, I am just pulling with a little force of suction on the water right at the top. That's all I'm moving, right? The only water that I am moving is the water that I have access to, right at the top. What makes all the water below it move? Well, because each molecule, like one of those dangling monkeys, do you ever have those as a kid, or you see those, the barrel of monkeys? Like the barrel of monkeys, each water molecule is stuck to the water molecules around it. So when I pull on this one, they all come with it. Now, that strength isn't absolute. It can be overcome. But as long as we don't give the water anywhere else to go, as long as we keep that tube intact, then we can use that force of suction to get water pretty high. Not infinitely high, interestingly. Ask Mr. Elaschuk. He can show you the calculations to figure out exactly how tall a straw you can possibly suck up with a vacuum. And after that, you need other forces to get the water up. Other forces like maybe capillary action, and like maybe root pressure, right? So it takes, well, that got worse. That got much, that I regret. I wish I had not done that. You ever do this thing where you think, like, maybe I'm making things better right now, and instead what you're doing is you're just making things worse? Yeah. That's the thing I do sometimes. Okay, there we go. So it's like a drinking straw. But evaporation at the top provides the force that draws water up. So it's like a drinking straw, but it's evaporation that gives us that. And then this is called transpiration. Transpiration. That's the name they give to it. And the plant can control the rate of transpiration to some extent. I'm going to say semi-control the rate of transpiration. I say semi-control because water evaporating. Will it happen faster on a hot day or a cold day? Good. Will it happen faster on a windy day or a slow day? Windy, right? Because the air will actually blow across that water and help it evaporate more quickly. So does the plant control whether it's hot or cold out? No. Does the plant control whether it's windy or still out? No. So it doesn't have complete control, but it does have some control. How does the plant control how fast the water evaporates? Hey, if you wanted water to not evaporate, so you had a cup of water and you're like, oh, treasured cup of water, I want you to not evaporate so I can drink you. What would you do? Okay, that would slow it down for sure because it's going to cool it down, but it still will evaporate in the fridge. What else could you do?
Maybe heat it up.
Heating it up will actually make it evaporate more quickly, but good thinking. What do we do with things if we don't want them to lose their moisture in the fridge? Okay, we could freeze it, fair enough, but assuming I don't want to freeze my water, because if you freeze the water inside the plant, you're going to have a problem. So what do? You cover it up, right? Isn't that what you do with something in the fridge? If you don't want it to lose its moisture content, you put some saran wrap over it, right? So a plant can stop water from being lost by covering it up. And the way it does that is what we call the stoma, or the stomates. This is the end point. These are the two cells that cover the opening of the xylem to the air in the leaves. And it's cool because if you look at a leaf under a microscope, you'll actually see them. That's a real microscope shot. Pretty crazy, right? And by pumping water into the stoma, an opening is created. And water can evaporate more easily. So this is essentially the faucet. This is essentially like having a tap in the leaf. And we don't just have one of them, we have thousands and thousands of stoma so that we can control how fast the water gets out. If we want water to get out quickly, we can open the stoma. And water will evaporate, and the water can move up through the plant quickly. If we want to slow down the rate of water loss, we can close the stoma, and then water will still evaporate, but it'll happen much more slowly. It has to wiggle its way through that closed pull. Does that make sense? What else do I want to say about that? That's all I want to say. This is actually interesting because, remember, the whole reason we move water is because, like, we need it up at the top, right? Right? We need it for photosynthesis and things like that. So when do we need way less flow? Photosynthesis. So we need water flowing when photosynthesis is happening. When does a plant not need that? Way less. Oh, come on. When doesn't photosynthesis happen? A little bit. Yeah, definitely. Winter, depending on the plant, but for sure. Nighttime. You can test this. Here's the thing. All of that pull, all the water pulling up, actually makes plants a little bit taller and a little bit skinnier. Even trees. You can test this. If you pick a tree in your backyard, nice big one, and measure around it during the daytime, when the stoma are open and water is being pulled up, and then measure around it again at nighttime. Some trees actually have a measurable slight difference, where during the daytime they get a little bit skinnier and a little bit taller, because that water pull, water being pulled up to the leaves, is enough to actually stretch the thing out just a little bit. Now, you're not going to see like it gain and lose like 6 inches or something like that, but there's a measurable difference, because that water has to get pulled up through it when we need it. Does that make sense? Now, it is pulling water, but the nice thing about pulling water up is that what can you put in that water? Anything you need to move. Does that make sense? So if you have a nutrient in the roots that you need to move up, no problem, just put it in the water. It's going to work its way up. Does that make sense? So this is a useful system for moving things around. Questions about that? This is called the transpiration tension theory of transportation in plants. It's how xylem, these dead tube cells inside the plant, move water up the plant. They do it by pumping water into the roots, by being made of small little tubes that naturally want to move water up the sides of them, and then by evaporating away water at the top of the tube through the leaves to cause transpiration pull, to pull more water with it. Now this means just to move water up, the plant has to lose some water. It's a naturally wasteful process. Does that make sense? There's no way around it. The way you get water up to the very, very top leaf of a tree, which can be way the heck up there, involves wasting some water. It has to be lost to the atmosphere, because the only way to get that pull, the only way to pull water up, is to evaporate some of it away. Does that make sense? Just nothing can be done about it. So, that's xylem. Now, xylem is very efficient. Very, very, very efficient. So xylem moves water very efficiently. Efficiently. But only in one direction. Phloem cells can move water in any direction. And again, we say they move water, but they can move with that water anything you want to put in it. And they can carry nutrients in that water. The most common thing we think of them moving is sugars are produced by photosynthesis. but have to be moved through the plant. But have to be moved throughout the plant. So how does it work? It makes a lot of sense actually how we move water up the plant, right? How do we move water sideways, down, maybe up a little bit? How do we move water anywhere we want, from one place to another? What do? Well, the answer is to have a whole second set of tubes called phloem, a whole second network of tubes. And then, inside that, we use something called pressure flow theory. So phloem makes a network of tubes. And so if I'm going too fast, let me know. Come on in.
Is there a handout?
Yep.
Do you have a Chromebook I can borrow?
Yeah, if you go to the back of Mr. Calford's room, you'll be... sorry, does it have to be a Chromebook? I have like the Windows devices.
It has to be a Chromebook.
I don't.
I mean, I think a regular laptop would work.
I think it would work for you. If you go to the back of Mr. Calford's room, you'll find a bunch. Grab one of those. And just make sure you get back to me by the end of the day. All right, Quinn? Thank you. Flow can be from anywhere to anywhere. Now, how do we do that? Do we like tell the water molecules, hey, water molecule, you're in the leaf right now, but I want you to get to the stem. And then the water molecule goes like, oh, okay, Joe, yeah, I'm on it, thanks. Is that how it works? Obviously not, right? So how do we do it? We do it this way. We do it by, this is accomplished by pumping water and nutrients into the source phloem and out of the sink. What? What's that mean? What does that mean? Well, it actually works exactly how your taps work here. Okay? Does the water know when it comes into the building that it's going to end up here? Do I go to the water at the main inlet valve to the building, which would be out in the front near the road, and say, okay, water molecules, you're going to go to room 80, and you're going to come out of the main sink at the back there? Is that what I do? No. Rather, way back at the pumping station, way back at the city, they just put a lot of pressure. They pump water in. Then how do I get the water to come here? I just start letting it out. I just let the pressure out. They build pressure up there, the whole system gets pressurized, and then where I want the water to flow, I just have to make there be a place where there is low pressure. Does that make sense? And here, the way I make there be low pressure is I just open it up to the air. The air is under way less pressure than the piping inside, and so all the water that's under high pressure says, oh, hey, whoa, there's a low pressure place, and it just flows. It naturally moves. Does that make sense? If you provide pressure at one end, and you relieve pressure in another place, it'll go there. And the nice thing is, it doesn't have to be just one place. I can say, I'm going to make a low pressure area here, and I'm going to make a low pressure area here. And where does the water go? To both places. And I could make a third place and a fourth place. And as long as I'm making enough pressure on the back end, it'll get to all those places. You know this instinctively. You know that you can run 2 sinks in your bathroom while somebody also does laundry and while somebody also takes a shower. But you probably also know, if your house is older like mine, and maybe doesn't have the best water system in the world, you also know that at a certain point, you can draw too much pressure and things stop working. I can take a shower and somebody can do the laundry, But if I take a shower, somebody's doing the laundry, and somebody goes take a shower in the other shower, all of a sudden not enough pressure for that hot water and I'm freezing cold. Except I win because my shower's in the basement. I'm the one who gets the pressure. Take that upstairs shower. But do you know what I mean? So this is how it works. Wherever you want to be the supply place, no problem. There, you just have to actively pump into the phloem. Does that make sense? And then wherever you want that to go, no problem. There, you just have to pump water out. Does that make sense? And if you do that, the flow takes care of itself. Does that make sense? So if you want to get sugar from the leaves to the stem, no problem. At the leaves, you pump sugar and water into the phloem. And at the stem, you just start pumping water out. And at first, you're just going to be pumping water out. It'll just be water. But quickly enough, that sugar that you pumped in up here is going to make its way down there, and you'll be pumping sugar water out. And as long as you do it, you'll keep the flow going. Does that make sense? So here's the basic diagram of it then. If we have like a network of tubes, you know, all these tubes kind of going this way and that way and that way and this way, doesn't matter. But say here is the source, and here is where I want it to go. Here's the sink. Does that make sense? And what we do is this. And when I say this is an active process, what do I mean?
It uses energy.
Very good. The cell has to actively spend some energy to do it. And then down here, just give me 2 minutes to finish this note, and then I promise I'll just give you the extra break time. Is that okay? Rather than break it up. So here we pump water and nutrients out of the phloem. And if you do that, then naturally here you're going to get high pressure, right? Because you're pumping in. And here you're going to get low pressure because you're pumping out. And fluids naturally move from areas of high pressure to areas of low pressure. And so you get the flow because of the difference in pressure. And the cool thing is that it'll actually flow quite directionally. The same way your pipes work in your house, which is all of this piping that isn't being used right now, it's just kind of pressure neutral, right? And so water's really not going to flow there at all. So even though these pipes are all interconnected, water doesn't go everywhere. It pretty much just goes where you want it to go. Because you have pressure neutral, those things don't really matter. It's going to go from where it's high to where it's low. There'll be some ancillary flow, but it overwhelmingly is quite efficiently works in the direction. The only thing to keep in mind is that these are active processes. This doesn't just happen naturally. The cell has to make it happen. They have to say, this is where we want to pump in, this is where we want to pump out. Which, it's pretty incredible that it's able to do that. It has a fairly robust control system. But there you have it. Does that make sense? And just really quickly, and then I promise I'll give you a 15 minutes break. If we look at the difference, these are dead cells. They're just tubes. All right? Xylem just grows into the right shape and then dies. Because it just needs to be a tube. It just needs to make, you don't want your pipes to be living, breathing things. You just want them to be pipes, right? If you think about a tree, the woody material, that's your xylem. right? It's just there. It's just there to hold water. So once it's grown, it can just kind of sit there and be solid and do its thing. The phloem, on the other hand, have to be living to actively pump. And they actually work by having the sieve tubes themselves. So they have these cells that are just tubes, and then they have companion cells whose job is to be the pump, whose job is to pump things in or to pump things out. And those are called companion cells. You don't have to worry too much about that structure, but it's important that you know that these have to be living because they have to actively pump, whereas these can be dead because the only place where the xylem has to be living is down at the root tips where it's actively pumping the water into the xylem. After that, it's just a tube. Phloem, on the other hand, because it's multi-directional, because the fluid can flow in any way it likes, needs to be living tissue. Questions about that? All right, I'm going to give you guys 15 minutes break then. In that 15 minutes, enjoy yourselves, have a bite to eat, do what you got to do. There's some follow-up questions here. In block 2, we are going to talk about our seed growing lab. Seed growing lab. Seed growing lab. It's a lab where we grow seeds. You could have told this from the title. The title is Seed Growing Lab. This is my song. Yes?
Could you send, when you have the time, could you send me a copy of the note that we just did?
Yeah,